Hi, I'm Bob. Let's continue solving the problems for Chapter 6, Multiple Regression Analysis, Further Issues. There were 3 models in problem number 7. I will choose the second model with the log of the total number of employees as an explanatory variable. First, the functional form allows a nonlinear relationship between the participation rate and the number of firm employees. We see that the log term in the second model and the quadratic term in the third model are statistically significant. So the last 2 models are preferred to the first linear model. Second, the coefficient is invariant to the unit change in logarithmic form, whereas it may contain too many zeros in the level form. So the second model is better than the third model for interpretation and reporting. Third, with the highest R-squared and adjusted R-squared, the second model fits the data the best. For the 8th problem, the answer depends on the purpose of estimation. Usually, we want to obtain the total effect of alcohol consumption on college GPA. We should not include the attendance rate in the model because attendance is very likely the direct result of alcohol consumption. They are highly correlated, and it makes little sense to estimate the ceteris paribus effect of alcohol consumption while holding attendance fixed. This is called the over-controlling problem. On the other hand, we should be aware that if we include attendance along with alcohol in the model, what we estimate is the alcohol effect on college GPA that does not go through attendance. For the second question, we should include both SAT and high school GPA in the model as explanatory variables for 4 reasons. First, they can explain college GPA and they are correlated with alcohol usage. Omitting these variables leads to omitted variable bias. Second, it will not induce a severe multicollinearity problem. Third, it reduces the error variance, leading to a more precise estimate of alcohol usage. Fourth, there's no over-controlling problem. Let's do the 9th problem. The calculation shows that the point prediction is always above the lower bound. As long as the standard error of the regression, sigma hat, is less than 3.92, the point prediction is in the 95% prediction interval. Sigma hat is the estimator of the standard deviation of the error term. We can find this value in the Stata result window. Stata calls it the root mean squared error, root MSE. In example 6.7 in the textbook, we regress the log of salary on the log of sales, the log of market value, and CEO tenure. The root mean squared error, sigma hat is 0.505, which is way lower than 3.92. Let's find the answer to problem number 10. The estimated coefficient on the log of expenditures is statistically significant at the 5% level in the first equation. It is not significant in the second equation. According to the first regression, a 10% increase in expenditure results in a 0.9 unit increase in the math test performance measure. The range of the math test performance measure, math 4, is from 18.9 to 100. So it's not a big effect. After adding the reading test performance variable to the model, the coefficient on the log of expenditures drops dramatically and becomes insignificant. Another strange change is the coefficient on the log of median family income. It has a huge negative effect on the math test performance in the second equation. It is more plausible that it does not significantly affect the math test after controlling for the other variables in the first equation. For the third question, the first equation is preferred to the second because adding the reading test performance variable to the model leads to the over-controlling problem. The reading test performance is also a direct result of the expenditure per student. It makes no sense to estimate the ceteris paribus effect of spending on math test performance while holding reading test performance fixed. Now, let's finish the last problem. Suppose the true model contains the quadratic term. The estimated equation is linear without the quadratic term. We can write it as follows. The new intercept alpha 0 equals beta 0. The new error term nu equals beta 2 times x squared plus mu. In the second part, the expected value of nu equals beta 2 times x squared. It depends on x unless beta 2 equals 0. In that case, the expected value is 0. For the third part, the covariance between x and nu can be written out into two terms. Both of them are 0. The second term is 0 because of the zero conditional mean assumption. The first term can be written out using the covariance formula. It is also 0. The covariance formula is as follows. So the covariance between x and nu is 0. In the fourth part, we use the probability limit formula 5.3. From the last part, we have the covariance between x and nu equals 0. Therefore, the probability limit of beta 1 hat equals the true parameter beta 1. In other words, the OLS estimator beta 1 hat is consistent. But it is not unbiased because the expectation of beta 1 hat conditional on x is not equal to beta 1. For the fifth part, the expectation of nu conditional on x equals beta 2 times x squared from part 2 at the point x equals 0. It is 0, and therefore beta 1 hat is an unbiased estimator of beta 1. The last question. For a nonlinear relationship between x and y, the linear estimation only fits the data around the simple mean well, but it has poor prediction at the tails of the distribution. Consistently estimating beta 1 and beta 2 allows us to capture the nonlinear relationship. Thank you very much for doing the problems with me, and see you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.